Vasista graduated, like he was from the batch of 2017, and he worked for a company which works on robotics for some time before going for
No,
a.
I
You work
didn't.
for the
I
company, right?
directly. No, I directly joined. No, I worked in Siemens before. I worked for Siemens for 3 months because my visa got
Yeah,
delayed. But yeah.
right. Yeah, Siemens. And then he went for his masters in University of Maryland. So yeah, that is Vasishta for you guys, and he's quite the guy when it comes to robotics. And so I just hand over this to Vasishta, bro. It's all yours.
All right. Uh, Good evening, everybody. As you may have heard, my name is Vasishta, and let's start. Okay. So a little bit. Can you see my screen?
Yep, yep.
All right. Okay. So a little bit about myself. I graduated in 2019. I got interested in robotics through my internship at IISc, where I was also working on path planning. I was working under a professor named Ashwini Ratnu in the autonomous vehicles lab. Uh, it was pretty fun, and that's where I solidified my interest in robotics as a whole. Then I went and did a 3 month stint at Siemens. That was on natural language processing, not nothing related to robotics or mechanical engineering. It was just to, I guess, I was joining within 3 months, and I didn't have anything to do for 3 months, so I wanted to do something at that time. Then I came here, and I've been studying robotics ever since. I came here this year, just before Corona hit. So first of all, I would like all of you guys. I mean, I hope all you guys are safe. I hope your families are safe and things like that. All right, so we'll start now. Okay, just a few guidelines before we actually start the presentation. Please take 2 minutes to mute your mic because generally what happens is if one of your mic is on, yeah, it's going to create some problems. So, just take some time, mute your mic. If from my side any issue comes up about video, sound, mic, anything like that, don't be shy. Go ahead, let me know. Don't wait for anyone else to stop me. Yeah, so about questions, I would highly prefer if all questions are through chat. If you type them to chat, it's easier for me to read instead of hearing a bunch of people talk over each other. I'll have a bunch of slides labeled questions where I'll stop for questions. So don't worry about that. That's when I'll answer all the questions. You can post questions anytime. Yeah, generally, what all questions are, welcome. No question is stupid. Yeah, in certain areas, I will go extra slowly because of lag. I guess because you're having a virtual meeting and some concepts need to be explained in a certain fashion, I will go a little slow in that time. All right. So generally, when you speak about a robot, it's a system of different modules and different entities and interacting with each other. In mechanical engineering, we generally learn about the physical system or the simulation module. We talk about the dynamics, how a particular force or a torque affects the x, y, z coordinates of the robot or its velocity and things like that. And all of that combined, comes in the physical model or when we are modeling the system. The physical model is nothing but like a math equation of how the robot is represented. Then you got the controller, which we learn in the control theory. I think people who have taken that subject, especially electronic students and mechanical engineering students in the third year, might know this idea. It's basically the simple idea is that you want to reach somewhere or you want to give a particular command. Or let's put it this way. You want the robot to reach coordinate x comma y, and you need to make sure that it goes there. So you need to give a set of commands or force commands like torque and force such that the robot moves from x1, y1 to your final position x comma y. So the controller does that. It creates a set of force and torque commands such that the robot moves from x comma y, x1 comma y1 to the x comma y. Then perception is a module which tells you where you are, or when I say you, I mean the robot, where you are, where obstacles are, where moving obstacles are, what is there in your environment, all these sorts of things. Generally, when we talk about perception, it is converting raw information into meaningful data. So, what is meaningful data for the robot? Your current location and your current location and the current location of the obstacles. It will take raw input images as it will take raw data as images, probably sound. Is basically different types of sensors. It could take lidar data, it could take GPS data, and then converts it into a meaningful thing. And then finally, we come to motion planning. Motion planning is the idea where you have all this meaningful data and now you have a goal. Now, how do I convert this more meaningful data into a plan so that I can fulfill my goal? That is basically motion planning. And that is what we will be talking today. Okay. So, in the most basic sense, motion planning is you're given a coordinate x comma y comma z in 3D space, and you're supposed to reach another point, say X goal, Y goal, Z goal. Okay, a perfect example of this is Google Maps. You know, you put in your initial location, you give it the final location, and it charts out a path for you. There are different ways you can do it. You can take the shortest route possible. You can take the longest route possible, all depending on what capabilities you have. I will talk about that in a few minutes. But I think the key assumptions that we need to make for path planning are the following. First of all, we already know the map. We already have a map of the environment. As in when we say we, I mean the robot has a map of its environment. It knows its current location and also knows its location at any point of time. That is a given thing. We assume that, and based on that, we work on the top of the thing. So basically, we have the perception module perfectly ready. Then we know how the robot behaves if you give it a particular command. The math model, as I mentioned before. So I think we can take an example of a car. We know for a fact that if you press the accelerator, the car will move forward. A math model will be a little more sophisticated, like how much accelerator will give me how much movement in forward direction. We need that in different quantities. It's very important that we know this. Suppose it might be possible that the car is in a reverse gear, and then when you press the accelerator, instead of going front, it will go backwards. So the math model should incorporate all this information in a way which is compact. It could be a differential equation, it could be a computerized function, it could be anything like that. Finally, okay, so we know the location of the obstacles and the open space around the robot that can move. Okay, yeah. So let's take a simple example. You're a self-driving car. You're in some location. You know where the buildings are. You know where the road is. So you know you can move on the road. You know you cannot move on the footpath. So all these things you already know. Now, what is path planning? Ideally, you want a path which will go from one place to another. All right, and in the most ideal sense, you want the commands itself. You want the force torque, or you want the how much acceleration I should press in order to reach there. All right. Applications. Obviously, self-driving cars and general robots. Yeah, robots which will be used in household to serve food or to do stuff. Airplanes. It turns out that pilots don't really know how to go from one place to another. They don't know if they have to take a left or right from that cloud, as in not the computer cloud, the actual cirrocumulonimbus clouds and all that. It turns out that because the Earth is not flat, if you take a map and you draw a straight line, you do not actually get the shortest path because the Earth is curved. In fact, you need to take this complicated sinusoidal thing. If you guys have ever seen that, you have to take that kind of motion. You have to go in that kind of motion to actually take the shortest path, and that's for airplanes. So motion planning is very important for navigation. Motion planning is super important for airplanes. It also turns out that robots that do surgery need to plan out how to move their motors in order to reach a particular organ. Suppose there's a surgical robot that operates on the hypothalamus or the prefrontal cortex or whatever, and the robot needs to precisely know that it needs to reach this location from, I don't know, this particular location. So mistakes in any of these could cost you, and different applications can tolerate different uh, tolerances to mistakes. So accordingly, we have to adjust our engineering to serve the purpose. All right. So I am guessing most of you are mechanical engineers. You guys, a bunch of you could be electronics, but I guess mostly mechanical engineers or mechanical engineering students. So what I'm going to do is I'm going to explain the idea of algorithms, because that's predominantly what motion planning is. It's like a bunch of algorithms, and then you choose them specifically for your application. Okay, so algorithms, they're like a set of procedures or commands that you need to fulfill so that something gets done. So sorting a bunch of numbers, trying to determine the different combinations to winning a lottery ticket, creating a binary tree, all these things. Uh, it's so you might think that algorithms is like a computer science subject, but technically it's more of a math topic, or at least I like to think it that way. And they're used in all different fields. It need not be only in computer science. For example, a simple algorithm in the mechanical engineering aspect is, okay, yeah. So I'm not sure if all of you have taken the subject called design of mechanical drives. Yeah, so every single thing that you do in that is a standard procedure. There is no out of the box thinking required for those kind of things. It's like, everything you do is limited. So we can write that as a set of solid instructions, and then we can let a computer run it, we can let a human run it, but technically they're solid instructions, and you don't have to mess with them exactly. So you can convert that into an algorithm. Yeah, as I said, path planning is nothing but learning a bunch of learning a set of algorithms, knowing their pros and cons, and using an appropriate algorithm for your very particular application. Okay. Okay. So, oh yeah, one more thing is, at the end of this lecture, the only thing you should definitely remember is the pros and cons of each algorithm, which I'll describe in some time. Okay. A note on visualization. So visualizing algorithms is a good idea to verify if they're right or wrong, especially in motion planning. If you need a system which can draw the map and which can draw the path on it so that you can see it with your eyes, it's very difficult to see what's happening if you're just seeing a bunch of numbers. So yeah. Okay. So before we actually get into motion planning, we'll just discuss a bunch of preliminary concepts, which I call environment setup. Okay. The first concept is task space and configuration space. So let's go to, okay, can you guys see this drawing app? Shashwata, can you see the drawing app?
Yes, we can see that. We could see the whiteboard.
All right, cool. So I'm just gonna draw a simple robot. Okay. Okay, so like this is a simple 3-arm robot. And you have the end effector, which is marked by an X. This position, you can, describe it as an X, Y, theta position. Pardon me for my bad handwriting. I'm using a mouse. Okay. Okay. And one second. Okay, give me a second. Let me finish drawing. Okay. Yeah. If you can see my drawing, you can see that there's one link over here, one link over here, and one link over here. You can describe the end effector in terms of x, y, and theta, or you can describe the end effector in terms of theta 1, theta 2, theta 3. It just depends on what's easier for you. But basically, the the meaning of the end effector remains the same whether you describe it in x theta y, x y theta, or theta 1, theta 2, theta 3. So this is the classical task space versus joint space or configuration space. So if you represent your end effector in terms of x comma y comma theta, then that's called task space. Basically, you're representing the end effector in terms of what you're going to be working with. Theta 1, theta 2, theta 3 are the joint space, or basically joint space slash configuration space, which basically means this thing. You're going to describe it in terms of the joint values, which makes life simpler in certain cases. And depending on your application, you might want to choose whether you want to use task space or configuration space. So the entire idea is, what are we going to work with? Are we going to work with the task space? Are we going to work with configuration space? Is a decision which is left up to you depending on your application. I hope that was clear. I think I'll give another example. Suppose you have a mobile robot this time. I'm just going slowly for this one because this is sort of important. So now the robot, oh, 1 second. Okay, so suppose you have a robot like this, and it's got like 2 wheels. Okay, you can describe it using the following set. You can describe its position by x comma y comma theta. In this context, you don't technically have a joint space for mobile robots or joint space slash configuration space. You just describe the robot in terms of x, y, and theta. For mobile robots, for manipulator robots, manipulator meaning robotic arms, you can describe it in theta 1, theta 2, theta 3, or x, y, theta. So the decision of what you want to work with matters for your path planning algorithm. For quadcopter, the task space will be x, y, theta, roll, pitch, and yaw. There are 6 different values which will describe its position and orientation. All right, so that's task space. Oops. Oh. Okay. Yeah. Oh yeah, I had a thing down here. Okay, so basically Q1 and Q2 are the angles, and if you describe the robot in terms of Q1 and Q2, it's joints. You're describing it in the joint space. If you're representing it using X and Y, it's the task space. Okay, discrete and continuous. Okay, so real life is continuous. However, computers work with discrete entities because they are digital. I guess it's similar to analog and digital signals, something like that. Depending on your application, you might want to discretize your continuous environment, or you might want to use a discrete environment itself, or you might want to work with continuous environment, keeping it as such. So there are different ways we can talk about. Then real time. Okay, so in certain areas you want real time. In certain areas it's not completely required. It's a decision which you need to take, and based on that you need to choose your algorithms. Typically in practice, anything that repeats itself in less than 0.1 seconds or 10 hertz, it's considered real time. Suppose I have a controller, a PID controller, and it runs, let's say, 100 times a second. So that's working in real time. Okay. The reason why this happens, I mean, there are huge implications. Obviously, you can't have your self-driving car think in the middle of the road. It needs to work in real time. Okay, shortest path. So shortest path is, okay, obviously we want the shortest path, but the question is, do we absolutely need the shortest path? Let's take 2-3 examples. Let's take home robots. Robots which will ideally work at home. They don't need to take the absolutely shortest path. Even if they take an extra turn or slight curve here and there, it's fine. But that answer quickly changes when you're working with robotic spacecrafts or Martian rovers or stuff like that. There, every bit of energy matters. So ideally, these spacecrafts want to take the absolute shortest path to save on energy. So that time you need to choose an algorithm which will give you the shortest path possible. Industrial robots. If you don't take the shortest path, it might take you some extra time doing your reaching your goal. which is going to be a huge cost to companies and factories and stuff like that. So industrial robots typically would want to use the shortest path and not waste any time there. Okay. Am I full screen, by the way? No. Okay. No. Okay. Never mind. Okay. So, pardon?
Yeah, no, you just asked now.
Yeah. Okay. So now we are done with some few concepts. Let's talk about maps. We assume that we already have given the map. However, we need a form of a map which can be read by a computer, because we're not going to literally give it, a picture of the map, right? Unless we have some image processing module. We are not going to give it a very complicated map. We want a simple map. Now, there are two ways to represent a map. Either you can represent it in form of a matrix like this, in terms of zeros and ones. And then, so this is the first method. Here, anywhere where there's a 1 that represents an obstacle, that means that the robot cannot exist in that particular coordinate. So this is the first row, second row, third row, and this first column, second column, third column, fourth column. We can, because the first this thing 0, 1. Okay, I'm using computer this thing indices. So there's going to be 0, this 1 is going to be in the position 0, 1, and you know for a fact that the robot cannot exist in that particular location. Okay, a simple map would be as follows, where you have 0, 1, 1, 0, and so on. And suppose the red goal is your starting position and your pink 0 is your goal position. You'll chart out a map in this form. I think that is pretty simple and self-explanatory. But the thing is, we need to represent map in sort of a way that the computer can read it. And this is one of those ways. The next way is, suppose, so this is clearly a discrete map, and obviously we'll be losing a lot of information if we work in discrete domain. So we can try it in the continuous environment. Suppose I define my obstacle as x greater than 5, x less than 0, y greater than 5, y less than 0. And I say if I have a coordinate which satisfies this particular condition, excuse me. If I have a coordinate which satisfies all these conditions, as you can see, there's a or, so I guess this is one single condition if you think about it. Then I'm not in the obstacle, I'm outside the obstacle. However, if I fail to fulfill this condition, then I'm inside the obstacle, and that's an invalid location for my robot. So this helps us in path planning. A simple example, this blue circle is my robot, and this red square is what this condition is describing. The coordinate x, y will satisfy this condition because the x value is greater than 0, y value is greater than 0. So it's a valid location. It can stay in that particular location and it can use it for path planning. Unfortunately, if any region inside, it cannot use it for path planning. Okay, so we talked about how we represent maps. Let's talk about how we can represent paths. So there are, I guess, I have learned 2 different ways to represent paths. Suppose I want to reach, okay, so let's say, okay, I think let's go back to drawing. Okay, so I have my goal location over here, and I want to reach x. X marks the spot, and let's say there's this huge obstacle over here which I cannot go. Okay, so the typical, I guess the simplest way to represent a path is a series of waypoints. So one like this, and then you can join it, and then you have a path. I guess that's, so basically I can represent, so this is my path. I can represent it as a series of discrete coordinates, and I can ask the robot, okay, fine, first move to the first coordinate. Okay, have you reached there yet? Cool, now move on to the second coordinate, and so on and repeat. So that's one way to represent a path. The second way is through a vector field. And I think the picture best describes what a vector field is. Okay, so this is an example of a, so S is my initial coordinate, V is my final coordinate, and this is my series of paths. A series of paths are also called waypoints, so I might be using them interchangeably. Okay. How do you? Oh, uh, okay. Yeah. So a vector field is technically a function where you give it x and y, and it tells you the direction you should probably move in. Okay, and you can define this function for the entire space of x, the flat coordinate or the 3D space, or r square, r cube, all that. You can define it for that particular space. You can define where the obstacles are in that space. For example, as I mentioned, x less than 0, x greater than 5 are all valid locations. You can define it in like that. And then what it returns is a vector. A vector is a direction where the robot should move. You can also give it a magnitude to tell how fast it should be moving in a particular direction. For example, over here, the vectors are pretty small. Here, the vectors are pretty large, means like, what, get away from the obstacle as soon as possible. So that's a vector field. So we can represent our paths using any of these techniques. And again, depending on your application, it varies and based on the requirement. Okay, obstacle avoidance. The question is, do we need it? Well, obviously we need it. So funny story, when I was working in IISc, I was working on quadcopters, and I must have crashed it at least like 50 times. The professor didn't know, so I'm happy about it. But yeah, that was a huge liability. Okay, so the question is, I think the better question to ask is it a good, what's your strategy if some random obstacle just pops up into your map? So you're a car, you're driving yourself to get ice cream or something, and suddenly a pedestrian, he or she randomly starts walking in front of the car. Now that's not there in the map. The question is, what are you going to do? And that is something you need to think about. Correct? So I won't tell you the answer what we should do, but I'll say, that's something you should probably think about. If you're in an industrial setting, obstacles are probably not something you worry about. If you're in an unstructured environment like the open road, then that's something you want to think about. So you need to adopt a few strategies. So let's quickly recap things we should consider for motion planning. The type of map, whether we want it to be real time, do we want the shortest path, how are we going to represent our map and our path, how are we going to deal with obstacles. All right, holonomic versus non-holonomic. It's not a super important concept, but it helps if you can understand. A quadcopter on your left or your right, I'm not 100% sure, but basically a quadcopter can fly in 3D space, and if you command it to move exactly up, it will move up. If you ask it to move exactly right, it will move right. If you ask it to rotate 90 degrees about its axis, it will do exactly that. However, on your right, you have a car, and if you ask it to move exactly right, it cannot do that. It needs to take a turn. And because taking a turn, it's constraining the motion in the y-axis with motion in the x-axis, we call it differentially constrained. And that's what reduces its capability to move. So when you're designing path planning algorithms, you should know what capabilities your robot has. If you give it a very weird path where you suddenly ask it to take a right or left turn and it can't do that, then we have an issue. So it's a good idea to know what all constraints or physical constraints your robot has in order to use it for the path. Okay, so I'm going to wait for 2 minutes for questions. Okay, how do you go to chat?
You just click on that icon with that green symbol, right?
This one? Oh wait, no.
No, top right.
Oh, there you go. I found it. Thank you.
Yeah.
Okay. How to find a function to define the vector fields? Should it be such that the gradient of the function must be given a motion vector? Also, I will discuss how to find out the function in, I guess, like literally the next slide. So yeah, I guess if no other questions, I'll move on. All right, cool. Yeah, I'll explain how to define those vector fields. All right, let's continue. Cool. Okay, so these are a list of algorithms which I'll describe now. So we're moving on to algorithms or the different ways we can work with this. Okay, artificial potential fields. Okay, so let us define something called a potential field, and I'm going to define it as a function u, which takes in coordinates x and y. Oh yeah, before that, we are assuming that it's a ground robot moving on the floor. So the coordinates are only going to be x and y, not x, y, z. Just 2D space for now, just to make it convenient. I'm going to define this function as the distance from the goal plus the summation of the reciprocal of distances from each obstacle. Meaning that if I'm near an obstacle, u tends to infinity. If I'm reaching the goal, u tends to a minimum. Sounds good? And the distance is defined by this function, square root of x minus x naught whole square plus y minus y naught whole square. I guess, is everyone clear with this? Yeah, I guess. Oh, is there any confusion with this? All right, cool. So if we define a potential field like this, what would it look like? It'll look like something like this. Okay, now all these spikes are where the obstacles are. It tells you that these are high potential areas, do not go there. And then the lowest potential area is the yellow dot where you have the goal. You are currently at the position green. Now you have to figure out how to move from green to yellow while avoiding these paths. Now, when you physically inspect it, it looks quite clear that if you just roll down, just roll down, it will eventually reach your goal. And that's exactly pretty much the idea. What we need to find out is a direction in which potential is decreasing at a maximum rate. So what we do, we take the potential, we find the gradient, and we move in the negative direction. That's pretty much it. That's all there is to this method. You just find out, you move along, and then you'll reach your goal. Yeah, just move in the negative gradient and you'll reach the goal. So what you can do is, as Darren mentioned, you can either A, compute the gradient at every single point of time, or you can pre-compute all the gradients in a vector field, store them as a function u star, sorry, u prime. Oops. Yeah, you can store them as a yeah, there you go. You can store the vector field u as a function of u prime. And u prime will be what will it be? It will be, I guess, it will be u prime x y will be the partial differential of u with respect to x I hat or I cap, I don't know what you guys call it, plus u y j hat, and you want to find the negative gradients. So you want to store your vector field as this. Just pre-compute it with your, like, write it down with your hand and put it as code. Do any way which is comfortable, and you'll eventually get this thing. Move around and do this. Okay, so let's move on to the pros and cons. If you pre-compute the gradient, you can just check it at any single point of time, which is potentially pretty good for finding, which is pretty good for real-time applications. However, there are two main disadvantages. Number one, and I think this is probably the one which is widely discussed, is the idea of local minima. Basically, when we move through the negative gradients, we are trying to find the global minima, which is the yellow spot. However, there are regions in the space where there's a local minima, the gradient is 0, and if your robot reaches there, it will have no idea where to go. So location is the red dot which I've drawn over here. If the robot by any chance reaches that kind of area, it will not know what to do. It will get stuck there, and that causes an issue. Number two is that your gradient might not be defined for all regions in space, and you need to mathematically make sure of that in order to not make your robot get stuck. All right, So any questions on artificial potential fields? It's a pretty simple concept. It's very easy to implement also. So if any questions, I'll just wait for 2 minutes, or not 2 minutes. I'll just wait for a few minutes. All right, cool. All right. So the next topic is breadth first search, and yeah, so a breadth first search is a search algorithm, or it's a path planning algorithm. It's used in path planning. It's a very fundamental not even rudimentary. It's pretty fundamental. It's what describes all the it helps you describe all the future algorithms in a very easy way. Breadth first search is used in computer science. I think it's a very standard algorithm in computer science, but it turns out for robotics, it's pretty useful too. So all algorithms which are related to breadth first search have two distinct components: initialization and an iterative step. So first, what we do is we initialize a set of things, then we describe an iterative step where for every iteration we do something. So if you can understand what the initialization step is and what we do in every iteration, we can just combine them and we'll get a decent algorithm. So let's start with the breadth first search. So for breadth first search, what we'll do is I'm going to draw a small map. All right, and now I'm currently over here. Now for simplicity, let's not assume any obstacles. Okay, so now what I'm going to do is I'm going to initialize something called a queue, where I'm going to put in stuff. It's basically a box, or you can. I'm pretty sure you know what a line is. Like when you stand in a line, the first person who comes in is the first person who's served by the I don't know, by the organization, or by the restaurant or whatever. So you have a queue of this thing. So let's say I have number 1, I have number 2, I have number 3, number 4. So let's assume 1, 2, 3, 4 different individuals, and they form a queue. I'll first serve number 1, I'll serve number 2, then I'll serve 3, 4, 5, and so on. So that's the idea of a queue. And what we'll do is we'll initialize a queue. We'll initialize an empty queue. So it's empty right now. We're not even going to put anything else. Then what we're going to do is you're also going to make a copy of our map, but we're going to initialize the values differently. So what we need to do is we need to keep record of where all we have already been. So this is number 1. This is number 2. All right. So yeah, now if I suppose in the future I visit this location, I'm going to put a tick mark over here, and I'm going to keep it that way. All right. So these are my 2 initialization steps. Now, what are we going to do? We are going to add our current location. So first of current location is 0, 0. And you're going to mark our, no, not yet. We're not going to mark our yet. So so we're going to add this, and we're going to enter the loop. And the loop is while the queue is not empty. So as long as the queue is not empty, I'm going to run this loop. Right now, it's not empty because there's 1 element in it. And so we're going to do the following. What am I going to do? First, I'm going to take the front element, the first element which is there. So right now it's 0, 0. So I'm going to take 0, 0 over here. Okay, I'm going to see from 0, 0, what are the different possible locations I can go to. I can go to 0, 1. I can go to 1, 0. Okay, and I'm going to make an engineering decision that I cannot move diagonally. So I guess these are my only 2 options. I can move right, or I can move right, or I can move down. So what I'm going to do is I'm going to do the following. I'm going to add it to my queue 0, 1, 1, 0. I'm going to mark the current location is already visited. So, I've already visited 0, 0. So don't consider 0, 0 if it comes up in the future. Okay, so now this step is done. Now, and of course, this one's also gone now. Now, what's the next element? 0, 1. So I'm going to go 0, 1. 0, 1 is this one. Okay, so my robot, or not my robot, I'm not moving the robot yet, I'm planning out. Now, I take 0, 1, I find out all the possible places I can go to. I can go to 0, 0. Oops. I can go to 1, 1. I can go to what is this? 2, 0. Or is it 2, 1? Or is it 0, 2? Yeah, 0, 2. Sorry, my bad. 0, 2. All right. Now, I will add 1, 1. I will add 0, 2. But I will not add 0, 0. Why? Because I've already visited it. And adding that to my queue will make me go into an infinite loop, which is not something which I want. So I'll add these two numbers. I'll mark the current one as visited, and I'll repeat. I will repeat until there are no more elements in my queue or I have reached my goal. So that is that's, I guess, breadth first search in a nutshell. What we'll do is we'll just, so I talked about visualization, and it is a good idea to see how it looks like in real life. So let's have a look at it. Can you see the screen? Shashwata, can you see the screen?
Yes, we can see the screen. I think Shashwata has some problems with the connection.
All right, cool. Okay, so you can see the screen. Okay, cool. Okay. So we assume that the blue one is a start goal and green one is a finishing goal. As you can see, it kind of checks literally each and every element along its path, and then it finally reaches the goal. After it reaches the goal, it backtracks to what caused it to reach that goal and then moves back. Let's consider this another example. So it just kind of draws a loop spiral around its location, and that's how it grows. It grows like a tree. It just goes around and it reaches its goal. So it's super important if we introduce, what's this? Okay, yeah. So if I consider, if I can consider diagonal movement, you'll see something like this. It's searching every single element in its node, and then it figures out that this is the shortest path. So one thing you might have noticed is that it literally searches every possible combination before it reaches the path. So this is called an exhaustive search because it literally exhausts its all possible locations. So now we'll look at a situation where there is a obstacle in the path. As you can see, breadth first search works with obstacles, so it's a good idea to use breadth first search, and it does give you the shortest path at any given time. So if you notice, it looks like as if you start a fire from the start position, the fire will, and everything is grass, it'll eventually reach the goal node, or you literally set everything aflame and move as if it's in a fire. So that's a way to look about this thing, a way to look at this thing.
I was looking at it as if you were filling it up with water and how it will reach that part. So yeah, that's almost like
that's a good idea.
Yeah.
Well, that's a good idea too. That makes sense. It literally fills up. Yeah, so basically that's breadth first search. So yeah, so these are algorithms. So this is the algorithm which describes breadth first search, and this is the consequence of that algorithm, how it actually looks like in real life. So it will be difficult for us to say, okay, fine, this is what I'm describing, but this was actually happening. That transition from what's actually happening to what we describe in algorithm is what we this is the reason why we need visualization, and this is something which I like to stress upon. Any technique that you try, you need to make sure that you can see it with your eyes. So yeah, that's breadth first search. You don't have to remember it. You just need to remember that it's an option, that you need to know that it checks every single possible combination, every single location in your map, and then it gives out a path. Okay, so let's move on to pros and cons. Pros: it is one of the fastest algorithms which we have. It guarantees the shortest path. One of the fastest. There are faster algorithms, and you might be imagining, wait, if it checks every single path, how can it be the fastest? Well, in a certain sense, it is one of the fastest. Uh, it is useful for maps without a terrain. So in all the locations which we checked, it had a flat ground. So if you know your robot's going to move on a flat ground, it's a good idea to use breadth first search. Okay, it tells us if path doesn't exist. Yeah, if your robot is completely blocked by walls or by anything, and you apply breadth first search to it, breadth first search will clearly fail. And that fail condition, you can use it to understand that there is no path to your given location, and then you take another decision to do what with that information. Now let's move on to the cons, or what are the problems with this algorithm. The number one thing is, because I prioritize all, so I am at location x 0, I have two options. I can move to my right, I can move right, or I can move down. Because it's a flat ground, I can move to both of these places with equal cost. However, if it turns out that 1, 0 is on an elevated location, while 0, 1 is on a flat ground. So for a robot, it might be easier to move on flat ground rather than an elevated location. And that is what breadth first search, or BFS, fails to describe. So it's not a good idea if your robot is on a terrain. Okay, second thing is, it's not fast enough for real time. Although it's one of the simplest and fastest algorithm, it will what's this? We'll check location. Yeah, okay. So it's not fast enough for real time. The reason why that is, if you saw the visualization, one second, let's go back to, I guess, yeah, okay. So we'll see this visualization. If you notice, I'm just gonna replay it one more time. All right. So as you can notice that the robot has planned everything around its region, and it also moved in a direction which is not in the direction of the goal. I mean, I don't need to check out this region at all, because I know for a fact that that's not where I'm going to find the goal. But it does it does search unnecessary locations. So in certain situations, that might not be the best idea. So any questions on breadth first search? All right, I'll move ahead. Oh, by the way, how much time has it been? Oh, is it feasible in real time? Breadth first search? Oh, that's a good question. So again, you need to see a bunch of different factors. It could be yes, it could be no. You need to see if you're working with so okay, fine. So basically it checks, if you go to this example, there are 9 distinct locations. So a computer can check 9 distinct locations within 0.1 seconds. So in this particular case, it's real time. However, if I have a map which is huge, it's got millions of rows and millions of columns, that time, if I want to plan a path, breadth first search might not be the best idea. That's number one. Number two, we're considering a 2D space that is only x and y. Now, if we introduce a third coordinate, the number of possible locations increases exponentially, which kind of drastically slows down breadth first search. So I would say not this algorithm. Don't use this algorithm if your number one idea is for real-time applications. I would not recommend using this algorithm. So I hope that answers your question. It's not like a hard, is it actually real time? It's more like a recommendation system. Like, yeah, this might be real time if you put it in this kind of situation, but it doesn't work in all situations. Okay, that's all right. So I think so. Relax a little bit because A-star algorithm is one of the things which I will go pretty deep into. This is one of the more useful algorithms is actually used in industry, and people actually like this algorithm. And yeah, it is similar to breadth first search with a few key modifications. All right, so let's start. The main features of A star are two things. One is a cost function where the planning algorithm is penalized to search in certain locations while not searching some locations. Let me explain. When I explained one second, so I'm just going to delete all of this. Delete. Okay, so let's draw a simple map like this. Just gonna go ahead. All right, cool. Let's say I'm in this location. Let's say that this location is not a wall, but it's rough terrain. Let's represent it as R. It's rough. So it's not a good idea to go for your robot to go in that path. And suppose now this part is completely blocked. Okay. So in reality, your map is going to be something very unclear. Some of them are going to be smooth. Some of them you cannot go at all. Some of them could be rough. You can go on the rough path, but it's going to be a little bit of a pain to go there. So what you can do is you can try avoiding it, but not completely. So a cost function will tell you that, you know what, if I go to this particular location, you'll have zero extra cost. However, if you go to this particular location, I'm gonna penalize you for doing that. So that's what a cost function is. That's number one. Another way you can look at cost function is, again, you have a car. Okay. Now for cars, it's easy to move straight. It's very easy. But it's kind of annoying to take a turn left or right. So what you can do is you can penalize certain actions. You can say, you know what, the less you take a turn, the better it is for you. So you can either penalize certain locations in the region, or you can penalize certain actions. And that all of that will come into something called a cost function, which I'll describe in a few minutes. The next thing is the heuristic. So a heuristic is like, so when I describe an algorithm, I know for a fact that the algorithm is absolutely correct. Like I can verify it with math. A heuristic is a guess. I'm guessing that doing certain actions will make my life easier. Like I'm guessing that if I study every day, I will actually get marks. I'm not 100% sure if that happens. Similarly, in this case, a heuristic could be, so if this is my goal location and this is my robot, I can give it a heuristic that, you know what, moving right is good for you, or moving up is good for you, or certain functions like that. Another simple heuristic is, you know what, I'm at this location, so I am 7 distances away, 1, 2, 3, 4, 5, 6 distances away from my goal. So anything which will reduce this 6 is good for me. So that is a heuristic. It's a guess. It doesn't work all the time, but it definitely helps you. Okay, that is, so now we have discussed we have discussed the idea of a cost function, and we have discussed what a heuristic is. Heuristic, again, it's a guess what we're taking, like, you know what, that's the region where the location could be, so I'm going to search that region more often. That's the basic idea. Now I'm going to define a term called total cost. So total cost is going to be an attribute of every single location. Every single location is going to have a total cost. It's going to have the cost of that location. It's going to have the cost of the action which takes to reach there. Also, it has a heuristic cost. Now, what I'm going to do is, instead of storing my locations in a queue like in breadth first search, I'm going to store it in a array or in a list. And for every single iteration, I'm going to pick out the location which has the least cost. In breadth first search, we picked out the location which came first. In this case, I'm just going to pick out the least cost. Or in a more sophisticated sense, it's a queue, but it's like VIP queue. More important people are served first, less important people are served last. Okay, so I'm going to get into a little bit of details of how the heuristics work, or how the A-star algorithm works. I'm going to show you a small demo, because this is something that I personally think will be important. Okay. So what are the requirements before we even think of programming this algorithm? Number one, we need a map. It could be discrete, it could be a continuous map, but you need a sort of a map representation. Okay, you need a function called getLocations, which will tell you from your current location x comma y, what are the possible valid locations you can go to from x comma y. Okay, on top of that, you also need the cost to reach that location. So if you're in x comma y, you need x plus 1, y plus 1, x minus 1, y minus 1, and so on. And you need to know the associated cost of going to that location. Number three, a heuristic function, which will take in your goal location. It will take in all the possible future locations, and then spit out something which will tell you that this location is a better location than this location to be in. Okay, and obviously you need a start and goal location. Okay, fine. Similar to breadth first search, we will have an empty matrix called visited, where we're going to keep track of all the locations where we have already visited. What I'm going to do is I'm going to initialize all the values to -1, meaning that they have not been visited yet. Eventually, as I start going through locations, I'm going to fill this matrix with the cost it took for me to reach that particular location. Okay, so in breadth first search, we use a queue to implement the first in, first out concept for this thing. For A star, we have multiple different data structures or different ways or different math to pick out the one with the lowest cost. One of the simplest one is something called a heap data structure. You don't have to worry about it too much. It's just something that gives you, if you're given a list, it picks out the one with the lowest cost. It's just for implementation details. All right. So what are you going to initialize? You're going to initialize all of the locations to -1, all of the visited locations to -1, meaning that none of them have been visited yet. And you're going to add your start location to the heap with the cost 0, because you're already there. There's no cost of reaching there. All right. Now, so iteration. So the condition is until we reach our goal or the heap is empty. What we're going to do is for every iteration, we're going to pick out the node with the lowest cost. We're going to mark that particular. Okay, by the way, a node or a location, I'm going to use them analogously. They both mean the same. They're a particular entity inside the map. Okay, so I'm going to pick out the node with the lowest cost on the heap. Take that node, check its visited value. If it's -1, I'm going to mark it with the cost of that. Then what I'm going to do is I'm going to check if that is what my goal location is. If it is my goal location, then I stop. I've reached my goal, or I've planned for my goal, so I'm happy with the results. If it's not the goal, then what I will do is from this location which I've picked out, I'm going to see all the different locations that I can actually go to. So for example, if I can move left, right, up and down, and I'm in the location 4,4, this function get locations will spit out 4,3, 3,4, 4,5, 5,4. So 4 locations, up, down, left, right. Then it's also going to spit out the cost associated with going to each of these locations. Now, I will also find the heuristic of each location. I'm going to add them up, and I'm going to find the total cost. After storing, I'm going to add individual location with that cost into the heap. I'm going to check visited. I'm gonna put visited if it's not been if it's -1. Oh, I'm gonna 1 second. Sorry. Yeah. I have these possible locations I can move from my goal location. And what my plan is, I'm going to add all of these locations to my heap. The condition which I use to add it to my heap is whether this location has already been visited or not. If that new locations which I get from get locations has already been visited, if it has already been visited, then I don't add it to my heap. If it has not been visited, then I add it to my heap. And then continue, repeat until I reach my goal. All right. So yeah, so it's not one of the more easy algorithms. It's a little difficult to understand, but let's try looking at a demo. All right. So we have, I'm just importing a bunch of libraries. HeapQ will help me keep track of all the nodes. Okay, so I have written this get location. It takes in the map, it sees visitor locations, and it takes in my current coordinate I comma j. It searches up, down, left, and right. It checks if this map is out of bounds. Like if I can go to a location -1, 1, that's out of bounds. So if it will not consider that. The map can have obstacles. So I'm gonna say if it is an obstacle, then forget about it. Like if 1, 1 is an obstacle, then I do not consider it in my get locations. And so this one pops up. It finds out all the possible locations I can go to, and it returns it as a list. All right. Now, I think the most important thing is the heuristic. So this is what I mean by heuristic. For a particular location, I get the heuristic as follows. It is the distance between the location and my current location and the goal. Okay, now there are two different ways to compute location. The one most commonly is the Euclidean distance, which all of you are familiar with, which is x squared minus y, x minus x naught whole square plus y minus y naught whole square, the whole root. That is what is Euclidean distance, the simple distance formula. This also comes something called Manhattan distance. Not going to get into it. It's simply, it also for a matrix, it tells you how many squares you're away from the particular goal location. All right. Now, A star. What do we do? First, okay, what's the first thing? We create a empty matrix called visited with the same dimensions of the map, and all values are -1. Check. We have initialized the visited matrix with all values as -1. With all the -1, which is the same location as my map, and I'm giving it the map. Oh, sorry. Before, let's take 2 steps back. My function A star takes in the map of the region, the start goal, the end goal. Using this map, I initialize my visited node and put all values as 1. I initialize my heap and I call it location. I put the start node and the cost associated, excuse me. I put in locations, I put in start, and I put 0 over here. And then I say until I reach my goal, or until the length of my locations, or until there are locations in the heap which I can still search. I'm going to do the following. So what is the first step? Pick out the location with the lowest cost. So I pick out the location. I pick out the location with I pick out a particular entity in the heap which has the lowest cost. And I call it current location, and it'll have a current cost. I will remove it from the heap in case it's not already been removed. That's some implementation. That's some Python thing. Okay, what is next? I'm gonna set the coordinate of visited to that particular cost. So I'm gonna go to visited at that particular coordinate of my current location. I'm gonna set it to the cost. Then what's next? I check if I'm already reached my goal. I check if current location is equal to my goal, then return visited. Then I'm okay. Then what else? Use get location to get a list of all new possible locations and the cost associated with it. Simple enough. Since I've written that function, life becomes easy. So this line, it'll tell me, I give it my current location, I give it the map, I give it visited, and it pops out all the possible locations it can go to. Okay. the most important part, the single most important part of A star is the following. For each node that pops out of get locations, for each location that pops out of get locations, I find out the heuristic cost and the cost of going to that node, and I'm going to add them up. So total cost for each location, total cost is equal to my current cost plus the additional cost to going there plus my heuristic. In this situation, I'm using Manhattan distance. You can use Euclidean distance, doesn't make a difference in the algorithm, but yeah, it helps out. And now, if the new location is a valid location, that means it has not already been visited before, it is not an obstacle, and it's not out of bounds, I push it to my heap. I put it in my heap, and then I repeat. Cool. So let's run this. And then obviously, as I mentioned, uh, you need a way to visualize the path and the map. So I'm going to start out this. All right. So I'm creating a map. Our map is equal to this huge matrix. So as you can see, there are some. I'm going to zoom in. Darren.
Yes.
Yeah. I'm going to. Is this clearly visible? The numbers.
Yeah, it's clearly
Yeah,
visible.
it's visible. Yeah.
All right. Cool. Okay. So yeah. So this is my map. I have 0, 0, 0. That means everywhere there's a 0. That means the robot can be in that location. Everywhere there's a 1. That means it's a wall. The robot cannot be in the location. I describe my start as 0, 0, which is going to be this point. I say my end goal is 0, 7, 7, which is the corner point. And now I run the algorithm. Oh, what's this? Oh, I haven't run the programs yet. All right, I think that should be okay. All right. So now, immediately you're going to see a few things. This is my map of visited locations. My initial cost was 0. When it moved over here, cost jumped to 14, 27, 39, yeah. Okay, as you can see over here, all minus ones. Why? Because initially in the map, all these were obstacles. So it did not bother checking them. So it goes down. As you can see, it starts growing. And once it reaches open space that's around this region, and you can see there's a bunch of zeros over here, it just spreads out everywhere. However, the most important thing is it spreads out in the direction where the goal location is. It doesn't spread out over here. It doesn't spread out over here. It kind of goes like this. And now for the visualization, I just printed out the path. So from here, I'm over here. It says go down. So I'm going down, 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 down. Okay, now it says go right, up. Now here I have two options. I can either go up or I can go right. So I'm just saying, okay, if I'm going to go take an arbitrary location, I go right, I go up, right, then down, and I reach my goal. Now, I think let's try this something interesting. What I'm going to do is, I'm going to, so by the way, I have a parameter over here, number of locations checked. Over here means 62. That means I have checked 62 different locations in this map before reaching my path. Now, what would happen if I comment the heuristic out and just work on the cost? Oh, wow, it actually reduced. That's weird. Oh, yeah, that's true. It does happen like that. Let's change the map a little bit. Okay. 31. 20. Okay, yeah. I think this is a better example. So I have to reach over here, and this is my starting location. Now, if I comment out the heuristic, where's that? Yeah. So I'm going to comment out the heuristic, and you will see that the number of locations checked is 31. Okay, so it goes and it directly goes in a way where you know the location is. Now what I'm going to do is I'm going to comment in the heuristic and see if anything changes. Okay, and then you see that the number of locations checked reduces to 20, and you can see that it magically figures out that this is the direction I need to move in. However, in the previous example, if you had noticed that if you use a heuristic, one second. All right, yeah. If you say, if I use the heuristic, I get 62 locations checked. If I comment it out, it says only 51 checked. That means it was better not to use my heuristic for this particular map, but it was better to use a heuristic in the other map. So this is where the guesswork plays, and this is one of the fundamental flaws in A star, which I'll get to now. Before that, I think I just wanted to show you how it looks like. So this is my implementation of A star. So yeah, if you can see, this is for a disk for a continuous space. This is my implementation of A star. As you can see, it kind of branches out to different locations and in search of the goal. So I gave it the goal of moving into the top right corner, and you can see it grows more in that direction. So yeah, that is another implementation of A star. Okay, so pros and cons. Pros, it's generally faster than breadth first search. Most importantly, since we can define costs for location and actions, we can use this for terrain maps or places where there's uneven movement. Another good thing is if there is no path, if it's completely covered, it will tell you that the path doesn't exist. It will give you paths in all the scenarios. Like in any situation, it'll either tell you there's no path, or it'll definitely give you some path which is decently short. Okay, the cons. It does not guarantee the absolutely shortest path possible. And if you notice, a bad heuristic can increase the time taken or the number of locations searched to check. Finally, and the most important problem with A star is that it does not scale to dimensions. Now, when we ran the demo, it worked pretty well for 2D space. So it's going to work well for cars, for ground robots. Now, if the size of my map is n times n, that means there are n rows and n columns, the time taken will be in the order of n square. But if I started using 3D space, I'll have n into n into n. It'll be n cube. That means the number of locations A star has to check increase exponentially, which can lead to problems because mobile robots, they generally work in X, Y, Z coordinates. But if you're going to use A star for a manipulator or a robotic arm, which got 6 different joints, you're going to have to search over a space of theta1, theta2, theta3, theta4, theta5, theta6. So that's n raised to 6, which can take significant amount of time to plan your path for mobile arms, robotic arms. Excuse me. So those are the pros and cons of A star. So any questions for A star? So I'm not 100% sure I haven't studied fuzzy logic, but no, it's not. It doesn't have any. I'm not 100% sure if it has any relation to fuzzy logic. I haven't studied it. But I guess you can use fuzzy logic to develop a heuristic. But yeah, any logic you can definitely develop a heuristic for that. But yeah, I'm not sure if there's any relation to that. Or at least I haven't heard of that. Why don't you start branching from even the end goal to start? That's a beautiful question. You're absolutely right. So, first of all, you can do that. You can definitely start from the end instead of the goal. It's just a matter of, it's again a situation-based thing. Suppose you are computing, it generally depends on the map, what kind of map you're working with. Right now, on the top of my head, I can't think of any particular scenario, but definitely you can do that. I think this is a good idea. So what happens is you branch out. One second, just give me a second. Okay, so suppose you have seen. Okay, let's just go to that video over here. Okay, so in a situation where my start position is fixed, but my end position is not fixed, then what I will do is I'll start branching out from my start goal and I'll create this sort of tree, and then I can pick out whichever goal I want over here, over here, over here, over here, over here, over here. I can pick it out and instantly I'll get the path. In the reverse side, I know exactly where I have to go. That is this endpoint, and my starting location can be variable. I could start from here, I could start from here, I could start from here, I could start from here. In that scenario, it would be a good idea to branch out from the endpoint. Very similar to what Chandran said. I hope I'm pronouncing your name right. Yeah. So you can start out in the you can start out from the end, and then you can store that visited node. This you can store this particular matrix and then reuse it for your future path planning requirements, which definitely saves a lot of time. So definitely that's a beautiful question, and of course you can do the same. We can do the same thing with breadth first search as well. All right. Any more questions? Absolutely, you can do it. Oh, sorry. I'm just gonna say the question once. So the question is, can you do path planning simultaneously from both sides? Something like start and endpoints are variable for algo. Oh, it. So, one second. One question. I'm gonna tackle Aditya's question first. Can one do path planning? Oh, okay, same from both sides starting. Okay, so you can sort of do it simultaneously, but that requires something called parallel computing, where so how so again, this is something like computer hardware stuff. When you ask it to do different things simultaneously, the computer eventually what it will do is it will put one thing in front of the other. It'll schedule one action and then do that first and then do the next action. The way to do it absolutely parallelly is to either use distributed systems or parallel computing, where you have things like GPU or multiple processors, where one planning from the start will go to one processor, planning to the end will go to the other processor, and then there will be a single matrix where both of them write to. So for the example, in this case, the visited node is there. I will keep it in the I'll store it in the RAM, and both these processors, which are where the tree is going from the start and where the tree is growing from the end, both of them can write simultaneously to visit it. Now, that will cause some issues, which I mean, generally there are some read-write concurrency conflicts, which I'm not going to get into, but it's generally not the best idea to use parallel computing. However, if you use serial computing, as in if you write a general program, it will alternate between these two. It will continuously switch. So if you're thinking of cutting time in half, it's not going to happen with a serial computer. I mean, as like a normal computer, but it will definitely happen if you're using a parallel algorithm. If you can parallelize this algorithm. But yeah, that's a good question, and that's generally something which people are looking at. Like there is research going on in this area, how to parallelize it so that in the fastest possible way we can do this. And this idea of starting both from the uh, from the beginning to and the end, and working with both of them, growing trees from both the sides, is I guess I mean it's a good workaround. So one more thing I would like to mention is these algorithms are standard. Generally in practice they use a modified version of these algorithms. So what you guys are suggesting, definitely it's used in real life, but I guess I'm not going to talk about what the real life scenarios are for this. All right. Any more questions? But yeah, I love these questions. These questions are really good. All right, I'm just going to take a minute because I think people might have questions. But yeah. All right. So if we go back to A star, one of the biggest problems is it does not scale to dimensions. So let's discuss an algorithm which will fix that issue, and that is rapidly exploring random trees. All right, so let's begin. Okay, so rapidly exploring random trees is not extremely similar to RRT. First of all, it's a randomized algorithm. So in in A star and breadth first search, we knew exactly what we were doing, and every step was calculated and done coherently. Here, there is an element of randomness, which sort of helps out actually. That's number one. There's an element of randomness. Number two, it does not actually search into every single location. In A star and breadth first search, in the worst case scenario, we will search every single possible locations. But RRT, not the same. Another good thing about RRT is that you can use RRT for continuous spaces. For real world applications, RRT works very well because, as I describe the algorithm, you'll understand. All right. So let's go to the drawing board. Where is the? All right. By the way, Darren, how much time have I taken? I don't want to take. I mean, if I'm going too slow, I'll speed it up a little bit. That's why I'm asking.
You've taken 1.5 hours.
Holy crap! Okay, I'm gonna. Yeah. All right. Cool. I'm sorry. I did not think it'll go 1.5 hours. But yeah, cool. Let's go and let's speed this up. Okay. So I have my starting goal. I have the starting point. I have a goal, and let's say this region is my obstacle. Okay. So what I'm going to do is the algorithm states something like this. First, pick a random location in the map. So this is the random part of the thing. So let's say this part. So, okay. Now I'm going to connect this thing like that. And I'm going to add a location in the direction of this thing. So I'm going to draw a location over here. And I'm going to connect it to this particular node like this. Okay, then I forget about this. Now, as you can see, I have a root node and I have a connection to it. Now I'm going to do one more thing. I'm going to repeat this process. I'm going to pick out another random location. And now, oh yeah, so now I have picked out my random location. What I do next is I find the closest existing node to this random location. In this case, it's the root node. So I'm going to connect it, move a step towards that, and then connect this thing. And then, of course, delete the rest. Oops. Delete the rest. Now, this is where the beauty comes in. I pick out another random location. Let's say, again, randomly just turned out to be over here. Now, I find the closest node. It turns out this is my closest node. So I'm going to connect it over here. And I'm going to take a step over here. Okay. And I make a connection. And I delete this. Okay. Now, what will happen? And as you can see that this is my root node over here. And you can see it's slowly kind of branching out in different directions. And if I continue doing this, if I start a node over here, I'll have a node like this, and then it'll start growing eventually like this. Okay, now if I have a goal location over here, if I pick out a random location over here, and then suppose this is the closest node. Now when I connect this, I try extending it, it's not going to be a valid node because this node is inside the obstacle space. So I will not consider it. And that's pretty much RRT. You continue doing that until one of the nodes is in the vicinity of your goal region. And I guess that's pretty much it. Yeah. Pick out a random location on the map, find the closest node to the location, create a new node in the direction of the random node, connect the new node, repeat. I'm just going to mute this. This is for sole purpose of visualization. Oh, that's not this part. Yeah, okay. So we start with the random node. We add an extra node over here. Then again, we add an extra node over here. Oh, by the way, the green circles are the random locations generated. So you can see as we increase the number of random locations, the tree starts growing. Eventually, it'll grow into the tree, and one of them will pop inside the region of your goal, and then you can find a path from that goal to your start location. As previously mentioned by Aditya and Chandran and Aditya, you can start from both directions, and there are variations of RRT star, RRT. Oh, close this. Where is that? Oh, I must have closed it by mistake. Oh, yeah, this one. Yeah. There are variations where you can start from both directions, and yeah, eventually your random RRT will span out the entire region, and then you can find path from any goal location to your starting node, and vice versa. You can find your location from any starting point to any goal location. So life is easy. So this is something called sampling methods, sampling based algorithms. You don't have to worry about it. And that's RRT for you. It's not, I think the best way to remember it is by implementing it. There's no way that you'll remember it after this lecture. So, so a variation is RRT star. So in the step where we connected, a node to the closest node, instead of doing that, I will connect it to the node which has the lowest cost. And by cost, I mean which is closest to the root node. So which is also in the same way. Okay, I'm going to connect. So I have this new node, and I have to connect it to the existing tree. I have two options. I can connect it to this particular node, which is technically the closest to my given node, or I can search in the vicinity of this node all the existing nodes which have the lowest cost. And it turns out that this node over here is inside the vicinity of this node, and it also is the closest to the root node. So what I'm going to do is I'm going to connect it to that. And what this does is it creates the path which it creates is much shorter. If I had connected this node to this node, then it would have been 1, 2, 3, 4, 5 steps from the root location. But now, since I connected it to this particular node, it's only 1, 2, 3, and 4 steps to the root location. So it significantly reduces the number of waypoints, and it also reduces the distance. So that's a simple extension of RRT star. So pros and cons. Pros and cons. Okay, so despite of the dimension, whether it's 70, 80, 90, 100D, it works pretty fast. You can use it for any arbitrary start points and endpoints, because once you have a tree, you can use that same tree for computing paths anywhere to anywhere. Now, what are the cons? It does not guarantee the shortest path. RRT star guarantees a shorter path than RRT, but not the shortest path. And the biggest problem is RRT and RRT star can completely fail in certain situations. So let's consider a map like this. You have the goal node in red, you have the start node in yellow. If you use an RRT algorithm for this, it'll generate all the random nodes in this direction outside this blob, and it will never penetrate through. The only way it can penetrate is that if there's an existing node over here, and it just happened that the random algorithm also popped up a new node over here, then it'll be able to penetrate that. But in certain situations, that's very unlikely to happen, and here's where RRT might fail. Yeah. So yeah, Ananya asked if this is method efficient because the branches go out in all directions away from the target. You are right. It does go in all different directions, and there are ways to make it efficient. But the general idea is we use RRT to compute for any given location, for any given node, and any given start location and end location. So in a way, it is a little inefficient, that is branching away from the thing. But there are workarounds around it. One good way, I would say, and I'm going to explain it to you, is so the random location generated is by using a uniformly random distribution function. That means the node can pop up anywhere in the space. A workaround that is to use a Gaussian distribution function with the mean around the goal location. What this does is it makes sure that the probability of a node popping up near the goal location is much higher than anywhere else. That means that the RRT, the tree from this algorithm, will grow towards that direction. So yeah, that's a good question. All right. Any more questions? All right, cool. Okay, so I'm just gonna quickly talk about something which I did last semester, and after that, that's the end of the talk. So what I did was I worked on RRT star, and I did a work. I worked on a variation so that it can be implemented in real time. So this is what I did. I use RRT star to quickly chart out a path, which is super like I guess my focus was get some path as soon as possible. That's what I did. After that, what I did was I told the robot to start moving. Once the robot starts, so, okay, so by the way, the path given is x1, y1, x2, y2, and so on till xn, yn. It's a very inefficient path. It's a very long path, but it's a path. It'll get you to the goal. And the thing is, you get the robot moving. While the robot is moving, you commit from x1 to xi, yi, some number of waypoints. You tell, okay, fine, you follow this particular path. After that, from the next waypoint, x1, xi plus 1 and yi plus 1 till xn, yn, I reuse the tree. I add more nodes to my RRT star. And since RRT star gives you a shorter path with as you increase the number of nodes, it finds out shorter paths for you. It eventually reduces the path length from xi to xn. That's number one. So I commit to a particular path and I start increasing the number of nodes for xi plus 1. Then I also tell it, so initially when I generated the first path, it'll have a cost. I say if I'm adding a new node and its cost is higher than the total path of my initial cost, then I chuck it. And using these simple ideas, I was able to get a much better, much faster path planning algorithm. So this is what you get in action. Yeah, so this is my project. This I think I did last semester. Just going to speed it up a little bit. Okay, so, oops. So it does its initial path planning in 0.22 seconds from all the way from here to here. It does that planning and it prints out the path length as 8.59 meters. And the time taken is 0.22 seconds. So this is the initial path which it found out. It's not super efficient. Oh yeah, so but as it's moving, it's continuously improvising and it's making better paths. And these paths are shorter than the previous ones. Now you can see that the path length has reduced to 8.48. Previously it was 8.59, which is like 10 centimeters of an improvement, but yeah, it's an improvement. It's reducing, and it has reached its goal. So what you can see is initially it had a path length of 8.59, but it actually covered 8.43, which is a decent reduction in the path length, at least considering that it is planning the path as it was going. You know, it's like when you study for your exam while you're going to the class, something like that. Okay. All right. Okay, so that's technically the end of this session. But you guys might be asking yourself, okay, fine, cool. I learned all this. Now, how do I get to a point where I can implement these algorithms? So for that, you need to learn how to code in Python. I would say Python for a bunch of reasons, but most importantly, it's easy and whatever questions you have on Python can be easily Google searched. Learn basic data structures and algorithms, trees, graphs, arrays. These are not, again, I want to stress that this is not coding. Coding is complemented to data structures and algorithms, but it's data structures and algorithms is more like a math course. So it's a good idea to know all these things. So for people who are interested in robotics, definitely learn Robot Operating System 1 and 2, the acronym ROS. I would highly recommend learning ROS 2. It's the new thing, and highly recommended. Okay, so unless you have a robot, excuse me, unless you have a robot within your reach, I would say stick to simulations, because because making a robot is a hassle, and if you make a bad robot, it's not going to be fun. It's not a good idea. And I guess the last one is kind of pointless, like get internships and do courses. But yeah, obviously, you should probably get an internship. I mean, you probably guys want to know how to get internships and all that. For that, get good GPA, and the general stuff, like what everyone tells you. Uh, yeah, I guess that's the end of it. Yeah. So if you guys have any questions, feel free to ask. That's the end of my presentation, by the way. Oh, general question. What's the difference between robotics and automation? I hear these terms used often together. Good question. So robots are physical entities, or at least not the ones which not like chatbots. I'm talking about the real robots, they're physical entities. And these robots, they can be semi-automated, automated, or completely manual. Okay, so it's a hard. The definition is not 100% clear of what makes a robot, but generally, robot is a physical entity. Automation is the process by which you make any machine, self like it can make its own decisions. So that's what automation is. Uh, Automation could be done to machines like vacuum cleaners or washing machines, but you won't call them robots. However, most of the robots are also automated. You try to automate them. So I hope that answers your question. Cool. Uh, yeah, I guess that's it. Yeah, I hope you understood the difference. Cool. Yeah. Oh, by the way, I wanted to ask Darren.
Yes, Vasista.
Yeah, listen, I wanted to ask you. Oh, by the way, this is the end of the thing. If you guys have any questions, keep them coming. But this is something else. Listen, I have a robot right now. Hello?
Okay. Yeah.
Yeah, so I made this robot hoping that it would work. It can be controlled from India. So I made a website and all that stuff, and I want to test it out if you have the time.
Yeah, sure.
Cool. All right, one second. I'm gonna. Yeah, this is the first time, so I'm not 100% sure if it'll work. So
Like, do you want us to try right now?
yeah, actually, or if not now, anytime else is also fine.
Okay, maybe you can share the link. Maybe.
Yeah, one second. Okay, so basically, it's going to take a little bit of time configuring everything. Is that fine with you? Or do you guys have time? I'm not sure what time it's in India right now. Oh, it's 8 o'clock. Or do you guys have time? Oh, that's a bit better question to ask.
I guess those who want can leave and yeah.
I just need one person. I just need one person to test it out. That's it. Like,
Yeah.
if people want to stay for that, that's fine. But all right. Where to get resources and tutorials on robot web tools apart from ROS Wiki? Robot web tools. I have not heard of that before. Robot web tools. What's it? I have not used robot web tools, so I'm sorry, I don't know anything about this. Oh, sorry. All right. I hope that wasn't too. I did not plan for it to be this long. I thought it'd be 45 minutes long. So I'm gonna stop sharing now. Uh, how do you stop sharing? Oops. Oops. Wait,
Okay,
am I still sharing
I
my
think
screen?
no, you aren't. You aren't. Yeah, no, you are. A bit.
All right, cool. All right, cool. All right, let's do
Okay.
this.
I guess before we go with the robot thing, I think we can give the vote of thanks. So
Yeah.
Shashwata, can you get it done with?
Yeah. Yeah. Okay, so the session is officially over, and thanks a lot, Vasishta, for taking out the time and taking organizing this talk. And thank you everyone who attended this talk. I hope you learned something useful and you enjoyed the session. So yeah, the rest of the session will be a bit unofficial. So if you guys want, you can. Thanks a lot.
Oh yeah, yeah. Oh wait, Sayak asked a question. What package did you use to connect your robot to a website? Did you use ROS? Okay, yeah. So what I did is there's a package in Python called requests, which will pull out. I mean, if you give it a URL, it will retrieve all the data from it. So what I did is I wrote that URL into my ROS program, and then I made a website separately, which will host all this information. So what basically the idea is